Hi everyone, welcome to third video of our series Statistical Testing using R. So today we are gonna be finally continuing with non-parametric tests. So we will be dealing with not normally distributed data, which is a relief after talking about parametric tests over the two videos very detailedly. So before we start, I want to again clarify what a non-parametric test is. So in statistics, we have parametric tests like ANOVA that rely on assumptions about the data's underlying distribution, and they often require normality and equal variances. But when the data deviates from these assumptions, such as having skewed distributions, having tails, by skewed that I mean, or ordinal data, non-parametric tests become essential alternatives. And they are robust in this case, making fewer assumptions about data distribution, and they focus on data ranks rather than raw values, which we'll also see during out this test. And then ranking here means that instead of using the actual data values, we sort them from lowest to highest and assign each of them a position or a rank. For example, if we have 15, 10, and 25, these would be ranked as 2, 1, and 3 respectively because of 25 is the largest value here, it gets 3. So let's start with our first test. Firstly, we have the Kruskal-Wallis test. Let me write the title before I talk about it. Wallis test. Oh. So this test serves as the non-parametric equivalent of the one-way ANOVA, which is, as you know, designed to test for differences across 3 or more independent groups based on their median values, which we've seen last time. And instead of comparing means in Kruskal-Wallis as ANOVA did, we examine the ranks of the data within each group, which makes it less sensitive to outliers or non-normal distributions because the outliers deviate from the mean a lot. But if we just rank them, then every value will have one unit difference between them. So from the median value of that rank to the outlier, it won't differ as much as it differed for mean. So let's see. So we use it when we have 3 or more independent groups, as I mentioned, and the dependent variable does not meet normality assumptions. For all the tests we've talked about, the dependent variable had to be normally distributed. And our assumptions is that the observations must be independent. Of course, this was our assumption for one-way ANOVA 2. The dependent variable should be at least ordinal, as the test ranks values across groups. And then this test is suitable for 3 or more independent groups, as I mentioned. So for 2 groups, we will learn how to use the Mann-Whitney U test, which is typically preferred for that. And then let's look at a real-life scenario. So a hospital is evaluating the effectiveness of 3 different rehabilitation programs for stroke recovery. As you know, stroke recovery means a lot to me because of my grandma. I've talked about it in my previous videos. So let's look at it. Program A has traditional therapy, Program B music therapy, and Program C virtual reality therapy. So the hospital checks the improvement in patients' mobility scores after completing their respective rehabilitation programs. And as you know, we have 3 groups here. In this situation, our independent variable is categorical, which is the rehabilitation program with 3 levels, Program A, Program B, and Program C. The dependent variable is the improvement in mobility scores, which is in ordinal scale, lower scores indicating a poorer mobility and higher scores indicating better mobility. After we conduct the Kruskal-Wallis test on this, if the results indicate a significant difference, which means we have less than 0.05 as our p-value, we can conclude that at least one rehabilitation program leads to a different median improvement in mobility scores compared to the others. And this finding would basically prompt the hospital to explore which specific programs are most effective, possibly leading to improved recovery protocols for stroke patients. And now let's test this in R. Think of it as you are a researcher. This is really cool how you can quickly test it. First, let me again control the randomness with a seed. Then let's define our programs. Again, we are turning it to categorical variables. Then we are, yes, we are repeating it again. We have a vector of program A, program B, and program C. And then we will repeat each one of them 30 times. Okay, now let's move on to our mobility scores. Then we will specify some samples 1 to 10. This will basically specify our 10 mobility scores, like our scala for choosing how mobility increases. Then 30 of each, place true. We use it because if it runs out of 10 numbers, then how will it create 30 numbers? It has to again give another example, like it has to again put 3 times, 4 times, whichever randomly it samples. So replace means you can use a number twice or more than 2 times. Then so here you can, with probe, you can actually specify with which probability you want that number to appear in that sample. So since we want the samples to differ, let's not give it random chance. Let's specify some probabilities for each 1 to 10 so that our samples can differ. For this, I've already given this in my article. I will just copy paste it here. It's basically the same. Let's take this. And then now we can finally create our data frame. Data frame. We put the program and then the mobility scores. Great. We can see our data. Let's first see it before implementing the test. So here you can see our data. We have for program A 3, 4, 1, 6, 7. If you look at the tail, we'll see the program C. Oh, my camera is everywhere. Sorry. And you can see the values for program C. Now let's actually implement the Kruskal test. Say Kruskal result, and then Kruskal dot test mobility scores is our dependent variable. Oh. And then we have the program as our independent variable, and then data is equal to data. If we print the Kruskal result, let's see what we'll see here. Can't put my camera here. Okay, now some values may really seem seem that you know them. For example, DF, do you remember it? It's degrees of freedom basically. Again, it's the same in this context because we have 3 programs, is 3 minus 1, 2. We have the p-value, but there is something unfamiliar here, which is the chi-squared. So the Kruskal-Wallis chi-squared is used to assess whether there are significant difference between the medians of 3 or more independent groups, and the higher value obviously suggests a greater difference between the groups' ranks. And let me show you how you can calculate it. So firstly, we combine all the data from all groups and rank them. Each value gets a rank based on its position in the sorted list. Ties, which means when we have the same number like more than 1 time, receive the average of the ranks they would have received if they were not tied. So for example, if we have 2 5s and they have the rank 6, if they weren't tied, they would have the rank 6 and 7. So we give them basically 6.5, which is 13 divided by 2. So we take the average. And then there is a formula for the chi-squared. I can directly show it to you because it's hard to say it. Here you can see the formula. We have the chi-squared statistic. N is the total number of observations. K is the number of groups. Rj is the sum of ranks for the jth group, and Nj is the number of observations in the jth group, and we see it like that. And the chi-square, let me put it again here. The chi-square can never be negative since the formula includes terms like Rj square. Since squaring any number, whether positive or negative, results in a non-negative value, all terms in the calculation contribute positively here. And important to remember again is that small values indicate there isn't much difference between the groups being compared, and large values suggest that there are significant differences among the groups, which leads to a lower p-value, obviously, because we are our alternative hypothesis says that the ranks differ across the groups. And then here we can see that our p-value is 0.14, which is not like less than 0.05. Since it's greater, we can't reject the null hypothesis, which states that there are no differences in the median mobility scores among different programs. But the thing is again here, how do we understand which groups are different from each other? Just like we have post-hoc tests for ANOVA, do we have post-hoc tests for non-parametric tests too? Yes, we have. And they are unfortunately different because they don't have the assumption that the data is normally distributed. So for this we have post-hoc tests like Dunn's test, and then what do we have more? Let's see. We have the Conover's test, and then we have the, was it all? I think that was all. Yes. Okay, then let's implement it. First of all, Dunn's test. Dunn's test is designed for pairwise comparisons following a Kruskal-Wallis test. It accounts for multiple comparisons by adjusting p-values and controlling the family-wise error rate, which is basically the probability of making at least one type 1 error. Because we are making multiple pairwise comparisons, we are susceptible to type 1 error in this case too. And you will see some familiar things here. I hope you remember them, like the Bonferroni correction, because we want to adjust our p-value for these. So by applying a correction, actually like Bonferroni, it controls for the family-wise error rate. And if I want to remind you, Bonferroni, it basically divided the p-value into the number of groups we had. And we use Dunn's test when the Kruskal-Wallis test shows significant results, particularly when the groups have unequal variances, which prevent the use of standard ANOVA and its post-hoc test. And when multiple independent groups are compared, especially if sample sizes are relatively large. Okay, now it's time to run it. I have actually given here some like not normally distributed data, so it might seem strange to you after always seeing R norm for a long time. For that we will use libraries like dplyr for data manipulation, and then again ggplot2 for visualization. And for this post-hoc test we have the library pmcmr+. Okay, now let's set the sample size as 30. Again, we have to set the seed to 3. And then let's define the groups. We first have group A, and then we put rexp function here. So basically this function generates right-cubed data for each group using an exponential distribution, and we'll see it because I will visualize it. We have 30 samples, we have a rate of 0.1, and since these will all generate the same data, since we have a seed, we can shift them by some value. Oops, sorry. XP. By the way, here rate is the reciprocal of the mean of the distribution. So if we have a higher rate, then it means that the events will occur more frequently, which will lead to a distribution that decreases quickly, and this results in more values being generated closer to 0, so it will be steeper. And lower rates like 0.1 we have given here, it will result in events occurring less frequently, which will result in a distribution that decays more slowly, allowing for more large values. So we have n, and then I have given the same rate. Let's give this time 25. I want to create a significant difference between their ranks. Rex P1 and rate 0.1 35. Now let's create our data framing and data.frame. We have the mobility scores, group A, group B, group C, program, factor, now we'll just give which program it belongs to. Program B, program C, and then repeat each 30 times. Okay. Now, oops, n times of course. If we change it, then it will be easier for us. Yes, I didn't forget anything. Now to show you how the Rex P, which gets random numbers from an exponential distribution, looks like, we will plot our data. For x-axis we have mobility scores, of course, and then will be a density plot. So we will see the frequencies in the y-axis. Let's fill it according to the program, so we will have different colors for each program. And then I'll plot the histograms too, so that we can roughly see the frequencies better, which we can't really see because it's more smoother in the density plot. Here, let's give for y density. Bins 15, alpha 0.5, because they will overlap most probably, and to see that we have to make it a little bit transparent with alpha. And then for position we'll give identity, position identity. So by specifying density here, before I forget to mention it, let me say it now. The y-axis is mapped to density, which scales the histogram bars so that the area under the bars sums to 1. So this will effectively convert counts to a density, which we'll use for density plot, and also allow for an easier comparison of distributions across different program groups too. And then we will have 15 equal intervals by bins. And for the position, we are choosing identity so that the ggplot2 overlays the histograms for each program rather than stacks them. Now, what do we... Oh, let's put our density plot. Here we'll just give the transparency as 0.7. Say facet wrap till the program. With facet wrap we will be able to split the plot by the values in the program variable, so we will create a separate panel for each program thanks to this. And then so if we give it with tilde, this will indicate that the program is the variable by which to facet, allowing for side-by-side comparison of the mobility scores distribution for each program. But you'll see all of these when I plot them. When you are plotting, you are looking at different kind of things to make it as beautiful as you can make it, which is good but kind of stressful. Distribution of mobility scores by program. Let's give an x-axis label, mobility scores, and then a y-axis label, density, team minimal. Should we give another team this time? Maybe let's give team dark. Let's see. And then you'll say scale fill brewer. If you don't know, look here, it gives it. Says that the brewer scales provide sequential, diverging, and qualitative color schemes from color brewer. So we basically give a color. And for this one, I've chosen set one in my article. Let's do that. Now let's plot this and see. Here you can see the dark theme too, and thanks to the facet trap, 3 different things. Look, we can also use this. Let's take it out. It's good to see the warnings if something is deprecated. Oops. After stat. So here you can see that they are right skewed because they have tails on the right side, and they go really steeply, as you can see, which is they go rather not really steeply. Sorry, I said it wrongly. Because of the rate. And what can I say more about? It's pretty clear here that's not normally distributed, and this is a good way of showing them on different scales. Program A starts from approximately 25, like it's mostly clustered around 25. The program B is mostly between 25, 50, and this is program C is mostly around 50, which we got by shifting these results by 15, 25, and 35. Now let's continue with the Kruskal test. Let me give it Kruskal test. It's really simple. We just say Kruskal.test and then mobility scores and program. I did it again. I always do this while clicking on tilde and date. So now we see our results. Let's interpret them before really going into how to actually see which groups differ. Because if the test says that there's statistically significant difference, then we need to look at each group. So here we can see that we have 2 degrees of freedom because we have 3 programs in this case. 3 minus 1 is 2. And then the chi-squared is 49.667, and then we have a p-value that is well below 0.05, which indicates that there is a significant difference. We also have a high rank difference, which we see from the chi-squared value. Now actually we can see if the programs differ from each other, which programs differ. For that, if you don't wanna look and then continue, you can directly say if Kruskal test p-value is less than 0.05, then do the Dun test. Let's say result, and then we call the Dun test function. And we again enter our formula in it, mobility scores till the program, our data, and we enter our method. So what can the method be? I've already given a hint about this, Spomperoni, to account for the type 1 error. Okay, after this you'll just see the Dun result. Let's say. Oops, what did I do? Not find function Dun test. Let's see. Is there a package that I didn't get? Upon looking at this, I realized I didn't have the package fsavg from which we take these values. SA. Let's install this. Now it's downloaded, and we can just call them library SA. Yay, now it works. And we can finally see the comparison. So now let's compare the programs. First of all, we have the z-value. Let's not confuse this with z-scores. Z-value is a measure of the standardized difference between the two groups. So in other words, it shows how far apart the two groups' scores are in terms of rank order. And the high absolute value, z-value, whether positive or negative, suggests a large difference between the groups. Here all z-values are negative, which tells us that the scores for the first program in each pair are generally lower than those for the second program in that pair. But we can be sure about that after looking at the p-values, of course. So how we calculate the z-value is, let me put it on the screen with this formula. Here R1 and R2 are the rank sums for the two groups being compared. Then capital N is the total number of observations across all groups, and N1 and N2 are the sample size of two groups being compared, and that's all. It's quite simple. Now, what do we have? We have the unadjusted p-values. So this p-value estimates estimates the likelihood of observing the difference purely by chance, without accounting for the fact that we are making multiple comparisons, which might cause type 1 error, as we previously talked about. That's why we adjust them. So we see that all unadjusted p-values are extremely small, which suggests strong evidence that the observed differences are not due to random variation. And then lastly, we have the adjusted p-values. We can see now that p-values that were adjusted using the Bonfermi correction control for the possibility of wrongly detecting a significant difference. But it doesn't really make a change here, because even after correction, differences between each pair of programs remain statistically significant since they are less than 0.05. Okay, now that we've understood these terms, let's look at each program and their values. For program A versus program B, the z-value is minus 4.225 something, and then adjusted p-value is, I will just look at the adjusted ones because they are more reliable in this case. It's like 0.0000716 or so, and it means the rank difference between program A and program B is statistically significant. And the negative z-value suggests that on average program A's mobility scores are lower than those of program B. And this might indicate it depends on our study, but the participants in program B, because we have a stroke recovery study this time, have better mobility outcomes compared to the ones in program A. And then for program C, the z-value is minus 6.997, and the adjust p-value is something like 0.0000782. And this again indicates a significant difference, and program A this time has notably lower mobility scores than program C, which suggests that program C is likely more effective in improving mobility. And then for program B versus program C, the z-value is minus 2.772, and the adjusted p-value is, in this case, 0.0167, and this indicates that there is a significant difference between the rank values in program C and program B, and the program C is this time, because it's larger, it has larger values than program B, more effective than program B. So overall we can say that program C tends to have the best mobility scores, and it's effective in improving mobility outcomes. Program A consistently has the lowest mobility scores among the groups, which suggests that it may not be an effective option for improving mobility. And program B scores better than program A, but does not reach the effectiveness level of program C, placing it in an intermediate position. So in this case, it would be best for the doctors or the researchers or the people there to utilize the program C, which was, I forgot what it was. which was the virtual reality therapy in this case, because it was the most effective one. So now we can actually move on to Conover's test. So Conover's test is generally seen as an alternative to Dunn's test, especially when dealing with small samples or when Dunn's assumptions are hard to meet. Because Conover's test is suitable for small samples where Dunn's test might lose power, comparing multiple groups when data ranks are available but normalized assumptions are not met, which we know from non-parametric tests, and when we are testing difference in medians among groups, similar to Kruskal Wallis test. And the thing is, Conover's test is better with ties than Dunn's test. Now we can actually implement this. It's also fairly easy. This time we use the KW all pairs Conover test. Give the mobility scores till the program that equals data, and then p dot just dot method is Parametric. Now let's see what results we get. Conover result. So this time we got a table which also shows clearly, and it says pairwise comparisons, and we remember it from the last time we used the pairwise t-test to look at this, and there we also used the p.adjust method parameter. So first of all, we have program A and program B, and the p-value for this comparison is 3.8e minus 0.8, which is much less than 0.05. So we can say that there is a statistically significant difference in mobility scores between program B and program A, and program B has, like, the participants in program B have significantly higher mobility scores compared to those in program A, which we've also seen here. And then for program B and program C and program A, and program C and program B, it's like the p-values are less than 0.052, so they have a statistically significant difference. So this basically is the same results we got from the Dunn's test. So we don't have to go much into this. We can directly move on to our second test, Mann Whitney U test, and we've talked about this in the beginning, saying that for two groups we can use this. This is typically preferred. It's another non-parametric test that is used to determine whether there is a significant difference between distributions of two independent groups. It's often used as an alternative to the independent t-test when the assumptions of normality are not met, because t-tests are used for two groups. So the assumptions are that the dependent variable is ordinal or continuous, the two groups being compared are independent of each other, and the samples are randomly selected, which is required for most statistical tests, including Kruskal-Wallis test, to represent population correctly. And then we use it when we want to compare the ranks of two independent groups and when the data doesn't meet normality assumption, in summary. So now let's look at a real-life scenario. Our research question is there a significant difference in weight loss between participants on diet A and those on diet B? In this case, the independent variable is diet type, which has two levels, namely diet A and diet B, and the dependent variable is weight loss, which weight is a continuous variable, so that works for our case, for this test. And then before this, I always want to talk about data types, so let's cover this quickly. So there are two main data types in statistics, categorical and numerical. Categorical data represents distinct categories or groups. It can be either nominal, meaning the levels won't have a specific order, like colors of cars, or ordinal, meaning levels will have a logical order, but without measurable distance, of course, between them, such as customer satisfaction level. All these scales we say, like disagree, slightly agree, or so. And then numerical data represents the quantities with measurable values that can be ordered. Numerical data can be discrete, which are counts or integers, as I've talked about in the previous or first video. They are specific separate values, and they basically have gaps between them and are used for counting, like saying I can't have 2.5 oranges, for example, or 2.5 sisters is a better example. You can divide the oranges, but you can't divide people, right? So, and then we have the continuous variables. Continuous variables are values within a range, have values within a range that are measured on a continuous scale with possible decimal values, such as height. We can have a 168.5 centimeter height, for example. And then, let's see. Now it's time to actually apply the Mann-Whitney U test. Again, we are creating two data sets. Diet A is rex p 30 samples, rate let's give 0.3, so that they have some skewed distribution. But for diet B, let's say p 30 rate 0.5 plus 20. This time we add some value to make them really different. Let's say weight loss data dot frame. Give our weight loss column, which has as a vector diet A values and diet B values. Then our other column is diet column, which will be the categorical variables. So we repeat diet A and diet B. How many times? Since we have 30 samples, 30 times each 30 times, and done. But I will of course plot it again. Say weight loss data and aesthetics, x is equal to weight loss, and for fill we will give the diet to get different colors for each diet. Then again we have our histogram, which has as y values the density. There's stat density, let's say 15 intervals, alpha value 0.5, position identical. Again, let's do facet, or before that, geometry density with an alpha value of 0.7, and then facet wrap. We have tilde diet. Let's separate these plots for each group. As a title, let's give distribution of weight loss by diet. For X label, we have the weight loss. For Y label, we have the density. Then let's use theme, maybe gray, and then again scale fill prover. This, let's see if we can use, let's use set 1. I haven't tried using set 2, if there is one. No, that's strange. Where did I put? Oh, unexpected in. That's funny. Okay, now it's done. The only issue, let me make it after stat. I directly got it from my article. And the set 2 also works, which is great because I like these colors more. After stat. Okay. Now As we can see, this time it's kinda steeper, and also this one is more on the left because we've shifted it by 20, and then they are not normally distributed, which is apparent. So to conduct the Mann-Whitney U test, we write Wilcoxon test, which might be strange because we also have the Wilcoxon test, but they are not the same. Just I will talk about, let me write this, data, weight, cost data. Okay, now that we conducted this, oops, it gave the results, that's great. So the Mann-Whitney U test and Wilcoxon rank sum exact test, as you can see here, are often used interchangeably because they are mathematically equivalent for comparing two independent groups, and that's why R uses the Wilcoxon test for testing for both of these functions, both of these statistical tests, and gives it as Wilcoxon rank sum exact test. So here we have the W as 0, which represents the sum of ranks for one of the diet groups, likely the smaller group if the sample sizes are unequal, but it's the same for this data set. And then this is calculated by summing the ranks assigned to each observation across both diet groups. So I'm thinking why we got a 0 this time, because we've used the same thing. That's strange. Let's see. A W value of 0 in this case says that there is no overlap between the groups, and the ranks of the two groups being compared are really different. All the observations in one group is lower than all the observations in the other group, which we have here. We can actually change this if we say 10, for example, and see the value again. Now see, we have some overlaps here. So now we get a W value of 23. This is still a relatively lower number, so we can say that most values in one group have lower ranks compared to the other group, and that there's a noticeable difference in distributions between the two diets. If we had said no difference at all and looked at this, the W value is really huge, which means that they might not be different at all, they might be the same. See, now they basically are in the same range. Let's make this 10 because it's a relatively good value. We have some overlap, so it makes it more exciting to see what the test will actually say. The p-value is really less than 0.05, which means that we can say that we can reject the null hypothesis and accept the alternative hypothesis, saying that the true location shift is not equal to 0. It's not, because we have shifted it up with plus 10, so it's not. And there's a statistically significant location shift between the two distributions. There is nothing more to say actually, and we see that the diet B has relatively better weight loss results than diet A. So as a result of this study, we can say that diet B is better than diet A in weight loss. Now I wanna show you. Oh, that was bad. I'm gonna show you something. Plus 10. Now we see this is more, and look, the shift is even more here. Okay. Because there might sometimes be a confusion saying if we increase A, would that be a negative value? And it's not, it just gives the positive value rank difference, because we are basically summing them up. The only thing here is that the we have to look at the density plot to make sure which diet is actually better. Now we can continue. What do we have now? We have the Wilcoxon signed rank test. And it's not the test that's equal to Mann-Whitney test. Please don't confuse it, because it's very different. So the Wilcoxon signed rank test is a test we use when comparing two related groups, not independent like the Mann-Whitney U test, where the data does not meet the normality assumption required for a paired t-test. So this is the equivalent non-parametric version of a paired t-test. And this can occur in pre- and post-treatment scenarios or any situation involving repeated measures on the same subject. Our assumptions are that the data must consist of paired or matched samples. Each subject should be measured under two different conditions, such as before and after treatment. The dependent variable should be ordinal or ranked or continuous, allowing for meaningful ranking of differences. And then the test should does not assume normality, but the distribution of differences between paired observations should be roughly symmetrical for accurate interpretation. And you can plot it if you want by taking the difference between the values and see if it's roughly symmetrical. In our scenario, let's say a fitness trainer wants to assess the effectiveness of a new exercise program on weight loss. A group of participants is measured for their weight before and after completing the program. And let's see if it works. Let's implement it. Call our library ggplot. You don't have to call it every time. If you want, you can. It won't make a difference. Set.c123 again, say n30 pre-treatment. Now I will show you another thing than RxP. I will show you our Laplace, because this will give more of a roughly symmetrical distribution, so the differences will also be roughly symmetrical. Say location 80, scale 5, and then we have the post-treatment, which logically needs to be less than the pre-treatment, so let's say our Laplace and location 5, scale 2. Okay, now let's combine it. Data.frame pre-weight is equal to pre-treatment, post-weight is equal to post-treatment. To visualize this, we have to actually reshape it. If we look at the data in this format, see. Oh, that was bad of me to do. And I forgot the library. Let me quickly find out. So to be able to use the rLaplace function, we need to install the package extradister, if I'm not pronouncing it wrongly, and then we can just call it with library. Let's say, no, let me comment this and call the library. Okay. And by the way, location 80 means the values will be centered around 80, and scale basically gives the how quickly the probability density falls off as we move away from center. If it's a smaller scale value, then it will be result in a narrower, steeper distribution. So I think this would work. Let's see. What's the problem here? Let me see from my code. The problem is because of I wrote something wrongly or not. Let's see. Still. So the problem was the parameters. Surprisingly, location would work, but I think I'm using a different package here. So the location parameter is for this rLaplace function called from this package. It's mu. If you remember mu from the known population mean in the t-test we've seen, the one-way t-test. can remember it from there. It was also center of distribution. Sigma is the scale variable, and then n is the same. So now this should work. Say mu and sigma. Okay, let's see. Finally, yay. So here we have the pre-weight and the post-weight. To be able to plot this though, we have to reshape it. Let's reshape to, here you can see flexibly restructure and aggregate data. Oops. Shape to create data using just to melt and decast or decast. We'll use melt in this case. And then data, say variable dot name, we'll give it treatment, and then we have the weight loss, actually value dot name weight loss or weight, what would work. And if we now look at the head of data long, you'll see how it reshaped it. So now we have the treatment, pre-weight, and then the weights, which is good for plotting because we will need the treatment and the weight columns for plotting. We will plot them as x and y axis, which we couldn't do in this case. Like even if we did, we couldn't have like divided as good as we can in this treatment weight structure, because we also wanna see the difference between them, put a different color or so. This is more convenient this way. Let's plot it. Data long, as x axis we are taking the treatment name, treatment. Then for y we are taking weight. For filling, we are filling with treatment. So we are giving different colors based on treatment. And then we'll use box plot. That's very funny. Let's continue, because in my article I have this code chunk, but I see a density plot. But we'll see. Wait, before and after treatment. Treatment, and then as x label we are gonna give the treatment, and then for y label we are going to give the weight as kilograms, and let's give team minimal this time, or classic. You never use classic. Okay, now let's visualize it. See. Oh, it actually gives like this. So we can see that post-weight median is relatively smaller than the pre-weight median. And what can we say more about this? The difference is roughly symmetrical. To see that, we have to use another plot. What if we say genome density? Let's see how this will work. Ooh. Let's just re-see this. Actually, we will need to change the things here. So this can stay as a box plot, and I can also plot for a density plot, because now we have to change the x-axis to weight and then fill it by treatment. Okay, now this can stay. Can create another plot, gplot data long x weight is equal to treatment density, it's equal to 0.7 gg title density plot of weight before and after treatment, and then you have the X label weight G, and then Y lab density, and then ST. Let's have like this time. Okay, let's see how this will seem. Okay, now this was what I wanted. As you can see, they are roughly symmetrical, so their difference will be also roughly symmetrical. And that was what I wanted with our Laplace. Now we can actually move on to the test phase. For the Wilcoxon results, we will use the Wilcox test, but we will specify that the paired is true, like we did for the independent t-test. No, paired t-test, sorry. Data, dollar, pre-weight, data, post-weight, and then we need to say paired is equal to true, and that's all. Now let's see the results. Here you can see the results. So what we have here is that we have the V. So V is equal to 462. This is the statistic that represents the sum of the ranks of the positive differences, so the post-treatment weights minus pre-treatment weights, and the specific value of V indicates the strength and direction of the difference between the two sets of paired observations. A higher value suggests a greater difference in this case, so it means that there is a great, there is this great difference between post and pre-treatments. And then for the p-value, we have this 9.31 something, but with e minus 0.9, so it's much less than 0.05, indicating a highly significant result. And basically we have a strong evidence against null hypothesis, which states that there is no difference between the pre-treatment and post-treatment weights. And as an alternative hypothesis, can say that true location shift is not equal to 0. We have a shift here. We have a difference here. So the exercise has a significant effect on participants' weights, as indicated by the significant change from pre-treatment and post-treatment. And although the V statistic indicates a difference, to determine whether participants lost weight or gained weight, we will need to examine the direction of the difference in the data. In practice, if we expected weight loss as an outcome, we would interpret this result evidence supporting the effectiveness of the intervention in reducing weight. And now it's time to move on to our next test. Now we have the Friedman test, and if I'm not wrong, this is our last test. Yes, it's our last test for today. That's good. So let's look at our Friedman test. This test is also another non-parametric test, which is used to detect differences in treatments across multiple test attempts. So it's basically repeated measures ANOVA, because we have more than two measures we take, and they are dependent. So it's not paired t-test. It's similar to Wilcoxon signed rank test, but it's with more than two samples taken from the same individual. Our assumptions indicate that the dependent variable should be ordinal or continuous. It measures the same subjects across different conditions or time points, and the groups being compared should be related or matched. This means that the same subjects are measured under different conditions or different times. And then while the Friedman test does not require normality, the differences between the groups should be symmetrically distributed to enhance the validity of the results, which also the Wilcoxon signed rank test required. So we'll again use the R Laplace for this. So we use the Friedman test when we have repeated measures on the same subjects and we want to compare their responses across 3 or more conditions, and of course when normality are not met, which prevents the usage of repeated ANOVA. So as our scenario, let's take the diet example again, but at another diet, the diet C, and make each participant try diet A, diet B, and diet C in different months, and see if there's statistically significant difference in cholesterol levels across the 3 diets. So let's test it. ggplot, oops, y, okay, library IDR set.c 1 2 3. Yeah, 10 participants. Is data.frame diet A rlab plus can actually have said and participants. It would be better. And let's give the mu 200, scale 15 maybe, or diet B. What should we give? Lab plus again and participants, but we want to create a different, so 185 maybe, and then scale 15, diet C, R lab plus part and participants. Oops. And even though I said that that's just like me getting used to it from the parametric test, we can't actually make a difference by changing the mean, because we rank the numbers and look at the ranks. Like mean doesn't have anything to do with this. And then scale 15. Okay. Data long. Now we'll wait. Before I do this, let me show you how the data is right now, and after I do, oh, again, no, oh, I said scale again. I keep saying this. It should be sigma. Okay. Now we have this diet A, diet B, and diet C, and we need to turn this into a format that we can plot. So for this, we will basically take the diet A, diet B, and diet C and give the corresponding values. But you'll see. For that, we have a really cool and easy function, just pivot longer, and we give our data. For columns, we say take everything from here, diet B, diet C, diet A, and names to make the names diet, column name basically, and make the values column cholesterol. Now if we see the data, it's different. Look, it looks much more like beautiful. We have diet A, its corresponding cholesterol level, diet B, diet C, diet A, diet B, diet C. It continues like that. Now we can plot this. Gplot, you have the data long. Statics. For x-axis, we have the cholesterols. For colors, again the diet. I can't see my code. Let me put myself here. Density, again a density plot. Alpha 0.6 because they might overlap. G title, cholesterol levels for each diet. As X label, we have cholesterol level, then as team, let's give BV now this time, and scale Phil Brewer, this palette. Let's see if we have set 3. I'm curious. Then let's look at the, what does it say? Each diet earn unexpected string constant. Oops, I did this accidentally. Yep, this must be true. Let's see. And yay, we have diet A, diet B, and diet C. with our Laplace, there might be some things like this, but don't worry about this. They are like mostly roughly symmetrical still to each other. And we also have a set tree, which is really good. I like these colors. Now we can actually do the Friedman test. Result Friedman dot test dot matrix. It's better to give it as a matrix because we have more than 2 groups. Let's see Friedman result. Okay. Dot test. Let's see. I don't have this either. That's what's wrong with me today. I have no packages. Now let's see which package this belongs to. We'll find out. Oh, I have this. The thing is, the problem here is that I know German and I wrote the whole name. It's just Friedman. It's normally Friedman in German, and you just write Friedman in English version. Okay. So again, now we have the Friedman chi-squared, which we had as Kruskal Wallis chi-squared, and we have 12.2 here. So this statistic is used to evaluate whether there are significant differences in the ranks across multiple related groups, which there is apparently because it's equal to 12.2. And then we have the degrees of freedom. Since we have 3 groups, it's 3 minus 1, 2. Lastly, we have the p-value, which is much less than 0.05. So we can say that we are rejecting the null hypothesis, and we are saying that at least one group has a significantly different distribution of ranks compared to the others, meaning that the 3 diets do not all have the same effect. Let's see now. For this, we will I think I can continue here. We'll apply the Dunes test here to see Friedman result. If the p-value is, we know this, but still let's try it like this, less than 0.05. If there's a statistically significant difference, then look at that with a Dunes test to see which groups are different, to understand which diet is better or the best. We have the cholesterol. Am I writing? Oh, no. Okay. Then we have the diet. Data is data long. Why am I doing this? Okay. And then we should adjust for type 1 error because we are making multiple pairwise comparisons, which we are using Bonferroni. And that was all. Say don't result. Why? Okay. If we want to make it complete, we can also write a little message saying no significant differences were found in the Friedman test. Dunes test is not necessary. Dunes test isn't necessary. Okay, but it's necessary in this case. What did we get? Cholesterol not found. Most probably I wrote it wrongly, which I did. Now we can see it. That's amazing. Okay, so no, not this. Where do we see it actually? Stable. Oh, now we see it. That's amazing. We again have the z-score, unadjusted p-value and adjusted p-value. So let's first look at diet A versus diet B. The z-score is 3.17, which indicates that the rank sum for diet A is higher than that of that for diet B, suggesting that participants on diet A have higher cholesterol levels compared to those on diet B. The unadjusted p-value is 0.0014, which is well below the conventional significance level of 0.05, which indicates that the difference between diet A and diet B is statistically significant. And then we have the adjusted p-value, which is 0.0044, which suggests that, again, the difference between diet A and diet B is statistically significant. And for diet A and diet C, we have a z-value of minus 0.2, which means that diet C is higher than, it's diet C, right? Okay, diet C is higher than that for, the rank sum of diet C is higher than that for diet A, which indicates that the participants on diet C may have lower cholesterol levels compared to those on diet A. And this again, this is not statistically significant, because as you can see with the adjusted p-value, it's equal to 1, which is well above 0.05. And then between diet B and diet C, the z-value is minus 3.3. So we can say that the participants of diet C have lower cholesterol levels than diet B, and this difference of rank sums is statistically significant. In summary, we can suggest that diet C is the, diet C is the best, because it's diet A is more than diet B and diet C is less than diet B. So less is the good thing here, because having higher cholesterol is a bad thing, and we say that diet C is the most effective. Finally, let's do a comparison. So Mann-Whitney U test is used for one of these tests. Mann-Whitney U, Wilcoxon signed rank, Kruskal, Wallis, and Friedman test are used for ordinal or continuous data. And for Mann-Whitney U test, the independent variable is the group and dependent variable is the outcome. For Wilcoxon signed rank test, we have paired values, so paired dependent variable before and after treatment. For Kruskal Wallis, it's independent, and for Friedman test, it's again dependent. So we use Mann-Whitney for 2 independent groups, Wilcoxon for 2 related groups or repeated measures, Kruskal Wallis for more than 2 independent groups, and Friedman for more than 2 related groups. And for assumptions, we assume random samples, dependent variables ordinal or continuous, and for Mann-Whitney and Kruskal Wallis independent samples, and for Wilcoxon and Friedman dependent samples. And so basically Mann-Whitney compares the ranks between 2 groups to determine if one group has higher ranks than the other. Wilcoxon compares the ranks of difference in paired observations to determine if there is a significant change. Kruskal Wallis tests if there are differences in ranks among 3 or more groups, and Friedman tests if there are differences in ranks across multiple related groups. And to see the groups that are different in Wilcoxon and Friedman, we do the Duns test or the Conover's test. And that was all from this video. Thank you so much for listening. I hope that you understood the concept clearly and that it helps in your future studies. So have a nice day, and in the next video I will see you with, I will see you with the compared proportions, what test we use for that, like the chi-square test. Okay, now bye and stay tuned for the next video, which will come soon.